All right. Hi, everybody. We're going to talk some more about wave behavior right now. Um, if you're following along in the book, this is the end of chapter 19. If you have the big book, it's the end of chapter 9. If you have the more condensed text, that is 3-hole punch that you put into the binder. So we're going to talk a little bit more, like I said, about wave behavior. We're going to look at the Doppler effect. We're going to look at bow waves, and we'll talk about shock waves. All right. So let's picture this is you. Okay, you're a star, and this is a sound wave. Okay. So what I want you to picture is that the source of the sound. I'm going to put a little blue dot. The source of the sound is this blue dot. I want that right in the center. And it's sending out this sound. And you can see it's going out in like all directions from the source of the sound. And it's going to you. Eventually, one of these dark circles are showing you like the crests of that sound wave. So eventually, as it spreads out, one of those crests is going to get to you. What would happen if, say, the source of the sound were not just standing there, source of sound standing still up here, source of sound standing still. What if, say, the source of the sound is moving toward you? Well, you're going to hear it a little differently. So what's going to happen is, if you're just standing still, this outer crest, say, will reach you, and then this inner crest will reach you. And I meant to say the source of the sound, we're just standing still. And then a little while later, this crest would reach you. Right? And that's going to be the frequency of that sound, how often you're experiencing these crests, right? But let's say, again, the source of the sound is moving toward you. Well, this crest will reach you. You'll experience that. You'll hear it. And then this one will reach you. And let's say these two sources of sound are emitting the same exact sound, the same frequency pitch, right? And then this crest is going to reach you, right? So these crests are going to be happening more frequently if the source of the sound is moving toward you, because this one started out toward you and it's going to reach you. And then this one is made while the thing is moving toward you, so it's going to reach you sooner than if the source of the sound were just standing still, like our top example. So the effect is, if the source of the sound is moving toward you, you will experience a higher frequency. So if the source of the sound is moving toward you, because you're experiencing those crests more frequently, it has a higher frequency. Source of the sound is moving toward you, higher frequency observed. All right. So here's another like cartoony picture representation of this phenomena. So this time we're showing, like you can see in the direction, that blue dot again is what is emitting the sound. So in the direction that the blue dot is emitting the sound, those crests are happening closer together. They're bunching up. The crests are like bunching up. And you know, if the crests are closer together, that's a higher frequency. But what's happening on the other side, where the blue dot that's emitting this sound, where it's moving away from? Well, now the crests are spreading out on the other side. So if the crests are less frequent, what do you think that means to how you will experience this sound? How will you experience it if the source that is emitting the sound is moving away from you instead of toward you? So look at this picture for a second. Think about everything we just talked about in the last couple minutes and try to answer that. Oh no, okay, stop doing that, stop. Okay, no, I really just want this, oh, I know how to do it. Don't worry guys, I got it, there we go, okay. So if the source of the sound is moving away from you, what is happening is you are going to hear a sound at a lower frequency. So moving toward, those crests are bunching up. Moving away, those crests are being more spread out. Here's another picture. So here we have an emergency response vehicle. An ambulance is the source of our sound here. So as it's moving toward our little figure standing right here, those crests are bunching up and they're going to hear a higher frequency. As it's moving away toward our little figure standing right here, those crests are being spread out and they're going to hear a lower frequency. So crest bunching, crests closer, crests further. So less crests per unit of time is lower frequency, more crests per unit of time is higher frequency. So this is what we call the Doppler effect. Okay, so this is what we call the Doppler effect, and it also applies to light. So you might remember, we already talked about this, light travels as a wave. So if whatever is emitting that light wave is moving toward you, what's going to happen is the crests of that wave are going to be bunched up and you're going to observe a higher frequency wavelength. If the source of light is moving away from you, what's going to happen is those crests are going to be more spread out and you're going to experience a lower frequency wavelength of light. There is something useful we can do with this Doppler effect. We can determine a star's spin speed by looking at how it's shifted. So there's an increase in frequency when the light source is approaching you, a decrease in frequency when the light source is moving away from you, just like with sound that we talked about. I am really tired of this. Please stay where I put you. What if I move it over here? Now, can you stay? No, come on. Please stay. Okay. So you might remember from your grade school days, or maybe you don't, we learned this acronym. We learned Roy, G, Div. And that is the spectrum in order. Remember, you learned red, orange, yellow, green, blue, indigo, violet. Red, orange, yellow, green, blue, indigo, nice deep blue, violet. And the next time there is a rainbow, if you see it, the colors will occur in that order. So that is the visible spectrum. All these electromagnetic waves move at what we call the speed of light. but these are the ones we can see, okay? So an increase in frequency we call blue shifted. And a decrease in frequency we call red shifted. So this is the low end of the frequency of what we can see where red is, and this is the high end of the frequency of what we can see where violet is. So what is a higher frequency, orange or blue? Oh, blue, because it's over there toward the higher end. Okay, so red is the lowest frequency that our eyeballs detect, and then violet is the highest. You have heard this term ultraviolet. That word ultra means above. And you have heard this term infrared, infrared. This term infra means below. So electromagnetic waves that are infrared are occurring at a frequency below red. Electromagnetic waves that are ultraviolet are occurring at a frequency that is higher than the violet light that we see. So, you know, that's why you put your sunblock on every day to protect yourself from these UV or ultraviolet waves. High frequency, it can hurt you. Wear your sunscreen. So like we just talked about, blue shift is that increase in frequency, higher frequency toward the blue end of the spectrum. And let's write this down again on this slide. Roy G. Biv. Red shift is when it is decreased in frequency and it's toward the red end of the spectrum. So if you have a star that is rapidly spinning, it'll show a red shift on the side that's facing away from you and a blue shift on the side that is facing toward you. All right. So the Doppler effect occurs for what? Sound, light, both of those, or neither of those? What do you think? So you'll remember my first example was the ambulance is making noise. Second example was light source. We talked about a spinning star. So you know now, and maybe you didn't know before, that it happens for both A and B, both sound and light. They both travel as waves. So now let's talk about bow waves. All right, so I want to talk about bow waves. We have super, that also means above. Supersonic aircraft, it flies faster than the speed of sound. Sonic refers to something that is sound. Super means above, so it's flying faster than the speed of sound if it's supersonic. A bow wave is what happens when something that is making a wave, and let's picture a water wave. So let's picture a boat in the water making a wave as it moves along the surface of the water. That bow wave is a V-shaped form of overlapping waves, and it occurs when the object that is making the wave is moving faster than the wave it's making. It goes faster and faster, and that's going to make a narrower and narrower shape of overlapping waves. And they have an illustration here at the bottom. So here, the thing making the wave is moving slower than the wave. So the velocity of thing making wave is less than wave velocity. Okay. And when we get out to here, you can see that they're equal, right? So there, that is showing you the thing making the wave has the same speed as the wave. Well, velocity, because we're counting direction here too. So here, velocity of thing making wave is equal to wave velocity. And here in frame C, the thing that is making the wave is just starting to go faster than the wave. And here in D, it's going a lot faster. So the velocity of the wave maker is much faster than the velocity of the wave. V of wave maker, much faster than velocity of wave that it's making. And even though if you're watching this, you're not sitting in class, I encourage you to take out your notebooks, take out papers, still write down. There is a hand to brain connection. It's why I'm talking and moving so slowly, so you have some time to absorb this and think about this. This is the kind of thing that you need to really think about and accept into your life, right? So I want you to still be taking notes, still write things down. So write down these things, draw yourself diagrams and pictures. It will help you. A shock wave is a lot like the bow wave that we just saw. So this, if we go back here and talk about this again for just a little second, it's called a bow wave because that's what the front of a boat is called, the bow, right? So when you get out in front of the wave, you have made a bow wave. All right. A shock wave is a pattern of overlapping spheres that form a cone from objects traveling faster than the speed of sound. So this is something moving through air instead of water. So we call it a shock wave instead of a bow wave, but it's like the same thing, except this time you're not making a wave in the water because you're a boat, you're making a wave in the air because you're an airplane. So you're an airplane, you are moving, you are crushing those air molecules up next to each other. You're creating a disturbance. It's a wave. And when you start moving faster than sound, you will make a shock wave. So this time it's overlapping spheres, like circles out, instead of just like we saw before, the circles, it's spheres because that disturbance is going out in all directions. So if we have an airplane here, trust me, it's an airplane. I'm not only creating a disturbance in the direction I'm going, that disturbance is headed out everywhere through the air, right? So our wave is spheres. So it actually consists of two cones. There's a high pressure cone at the front of that aircraft right there, and there's a low pressure cone that follows at the tail of the aircraft, because here I've bunched everything up together, and here I've spread it apart. I've pulled it apart, kind of. So it's not required that that airplane be noisy to make that shock wave. Okay? The airplane could be silent in its operation. You would still know when it passed you. You would feel that pressure and you would hear a crack. So the sonic boom is that sharp cracking sound that is made by a supersonic aircraft. And you maybe have, or you maybe haven't heard a sonic boom ever. But another example of a sonic boom is the crack of a circus whip. So if it's long enough, what happens is when you crack that whip, the tip of it is moving faster than the speed of sound, and it will make a sonic boom. So another example they give is a supersonic bullet. I don't know if all bullets are supersonic or not. Okay. So, and then I just have some questions for you. A wiggle in both space and time is what? A vibration, a wave, both or neither? You should pick wave. All right.